Pleasure to be here. Thank you for inviting me and giving this lecture. I approach this topic with a certain amount of hesitation because my domain of work, while intersecting with AI, is not quite artificial intelligence. So I'm not sure. I'm still not sure whether I can do a good job of explaining what AI is and where it is going. I have tried to make it as uh, simple as possible. I mean, removing all possible equations everywhere I could. In the process, it may have become, and I'm sure it has become, far too simple for the experts sitting here. So, my apologies in advance. This is going to be not a very technical talk. What I have tried to do here is to give everyone a sense of what AI as we understand it today is, how it has evolved over a period of time, where we are today and where we are likely to go to. There has been a lot of popular articles on AI. Today it's probably the buzzword. Everybody seems to be working in AI, at least in computer science. And there is, of course, a lot of funding associated with it, which explains the first statement. There is certainly a lot of content that is there, which is the substance part of this talk. At the same time, there is a lot of hype around it, which at least some of it is quite unwarranted. So I would like to touch upon some of those aspects also. So let's start right from the beginning. The advent of artificial intelligence is really the story of computing. It has been long discussed, and it has been a great fascination for researchers to understand the mechanics of human brain. The formalization of this, that how exactly the human brain operates and how simple can we make that operation too, led to the Turing machine model of computation proposed by Alan Turing in 1930s, which kind of whittled down all the complexities and came up with a extremely simple model of computation for any kind of computation, that is. And he showed it to be as powerful as any other model. And that is what led to a famous Church-Turing thesis that even all future models of computation we would come up with are equivalent to the Turing machine model. While the Turing machines provided the theoretical groundwork to our understanding of computation, that how the brain operates on one aspect, there were also studies being done on understanding exactly the structure of human brain, and that's where the concept of neurons came about. And I'm sure biologists here know about it much more than I do. And these neurons were supposed to be scattered, or rather forming the entire brain with lots of interconnects of all kinds. And I'll come down to that later, that the way this notion of neuron was abstracted out into something very simple, and that has certainly led to a lot of progress in artificial intelligence. But just the fact that the entire brain was viewed as a collection of large number of neurons which were connected in certain way, this allowed the possibility of this abstraction, which led to the thought that maybe we can create an artificial device which would do something similar. This was partial motivation towards the discovery of computers in 40s and 50s. In 50s, the first computing machines, or general purpose computing machines, were constructed, and they almost immediately started doing certain tasks which were beyond the capacity of humans, like doing large arithmetic, uh, which humans were not particularly good at, but computers were really doing fabulously well there. Uh, some of these things led people to believe that computers are now the next step in the evolution of humans, and they are going to replace humans very shortly. And there is a super intelligence being which will come into existence, and that time is not too far. In fact, many predictions were made giving specific years, that by this year this will happen, by this year this will happen. So that's where we were. Like by end of 50s, there was tremendous excitement that the computers now are going to do wonders. Uh, so this is the story. Our story really starts from there, and I have broken down this story into this last about 60 years have gone by since then, into 4 sections, separated by, in a couple by decades. The 2 decades. The first section is 60s and 70s, when there were all the foundations of artificial intelligence were laid. There were tremendous expectations, which ended up in tremendous despair. So let's see this part. Like I said, the neurons were the building blocks, are the building blocks for our brains, and these neurons were abstracted out very simply as what we call threshold gates on the more technical side, but more commonly known as perceptrons. These are simply a, a gate or a function which takes as input some n variables, each taking the value 0 or 1, and the output of this function is just a linear check on this. You do a weighted sum of these values and check if this sum is greater than a given threshold weight. If yes, the output is 1. If no, the output is 0. Extremely simple idea. And the thought was that you have this gates, which are a large number of gates are connected in a certain way, and that's what there is to computing. And it was indeed shown that this is all there is to computing. Enough number of gates of this kind can do any task. Now the question really was, how do you build it, and how, more importantly, how do you ensure that it does all the computing tasks that you want it to do? The second question, that how do you make it do what you want to do, is what led to this idea of machine learning. That we have this collection of threshold gates or perceptrons, but we don't know a priori what weights to assign to each gate. And therefore, given a specific task to perform, why not learn from that task what weights should be there? So a natural idea is that take a set of inputs and corresponding outputs for doing a special, which are connected to a specific function, and use this input-output behavior to figure out what those weights should be for this collection of threshold gates, which should as closely approximate the given function as possible. And this is what the notion which we call today the supervised machine learning is. That this setup learns how it should behave by suitably fixing the value of the weights. And this is a very fundamental notion that has had a tremendous impact in the development of AI. This led to what we again call today neural networks, that you have multiple layers of these threshold gates connected with each other. Each gate has certain weights, and then again use that input-output behavior to learn weights at all levels. The only problem was that learning these weights required very significant amount of computation, and the computers of the time were really not capable of doing that computation. In any way, this such kind of collection of gates with multiple layers is what is called neural networks. Again, a very important notion which will play a very key role in future. Another concept that was invented at the time is what is called backtracking. And when it came about, it led to tremendous excitement around it. Now, because this was a very general notion, which allows you to solve any search or optimization problem. You have a search space which a very large, potentially very large number of possible solutions. So you start your search at any point and go take a certain direction in your search. And if you find the solution, well, you are done. If you don't find the solution and you get stuck somewhere, you just retrace your steps and take another direction. A very simple notion, but it turned out to be fairly useful in solving certain limited problems, that is, which did not have a very large solution space, or which had very structured solution space. So initially it met with a lot of success. So that was also, so predictions were made based on this as well, that this is a grand tool which can literally solve any problem we want to solve. Another very general notion that also came about, which was influenced with the theory of evolution, is genetic algorithms. The basic philosophy behind it was that the nature has used evolution to come up with very powerful computing machines, which are us humans. Therefore, let's use the same evolution or evolutionary process to come up with algorithms which hopefully will be very powerful and which can solve a lot of problems. So again, this method searches a large solution space. It starts with a small set of potential solutions. The thing here has to be that you can grade the solution, how good a solution it is. So it's more like an optimization problem one is trying to solve. So you start with a few bad solutions. You want to go to a good solution, which is a much higher value associated with it. So the way to do it is you apply what we believe is how the evolution happens, that you have this genetic material which a collection of them. There are crossovers which happen with certain probability, and mutations also happen with certain probability. So it transforms the collection to another collection. Then the selection happens, that you throw out the bad ones, continue with the good ones, and repeat. So exactly the same process is mimicked here, and with the hope that this process will lead to very good solutions. And indeed, this has worked very well in number of engineering problems over time, where you want to find a good solution. So with all these tools in the kit, since we want to mimic humans, that's why it is called artificial intelligence, these were applied to a number of human tasks. The primary human tasks, or intelligent human tasks as we call it, are, let's say, vision, speech, ability to analyze and logically take something to its conclusion, even walking through an obstacle course which analyzes the possible obstacles and finds a path to avoid it in a fairly quick time. So these are the main tasks. So for example, for natural language to understand, to make computers understand it, concepts were evolved which you borrowed from the grammar of a language, that what are verbs, what are nouns, how are sentences constructed from this, how are multiple sentences brought together, and they were modeled as graphs, which connections between them, and the hope was that we can use this, what is called a semantic net, to understand what a sentence or a phrase means, and then based on that meaning we can do specific tasks. For example, translate it into another language, the same with carrying the same meaning, or perform a certain task which that sentence asks us to do. Again, some initial success stories were there. For example, a program called ELIZA could actually carry out fairly realistic conversation with humans. For the task of movement, which are again commonly known as robots. So robots were constructed who could move and also see. So they could see, visualize or take a picture of the surroundings and make their decisions according to that, and make it. But these are all kind of were fairly limited, but that was not surprising. In any new domain, you initially have low-hanging fruit which you can quickly solve, and then as the field evolves or develops, you do more and more sophisticated things. So that was the hope, that we have started well. We will scale it up fairly soon and fairly quickly to something much more significant. None of these were met. By the end of 70s, people came to a realization that the approaches that were being used and the expectations that were associated with it here are just too unrealistic. They just cannot solve what we want them to solve. All these tools just fail to cross a certain threshold. With backtracking, for example, it was very soon realized that when the search space is very large, your backtracking will just go on forever. It can't do any intelligent figuring out the solution. Same issue with genetic algorithms. They just fail to scale up. Neural network, I already mentioned that when you have a large number of gates, then even the learning becomes a challenge. You cannot learn it properly. The natural language models also failed quite spectacularly. But just couldn't go beyond a sentence or two. Even simple sentences, they couldn't even understand a complex sentence. Now, there was a strong theoretical reason why this was happening, which was demonstrated by this parallel development in the theory of algorithms and complexity theory, that most of these tools, the problems they were trying to solve, were inherently hard, as we call them today, NP hard problems. These are the problems which there is a very strong reason to believe that they cannot be solved efficiently. And these tools were trying to solve those problems efficiently. So clearly, it's not going to happen. And that was quite a major disappointment, because it's like realization hits you in your gut that, man, it is just not possible what we are trying to do. And that really set everything back by quite a big margin. Because the expectations were so high, the disappointment was equally big. And the funding stopped, people moved on, and it kind of required a reboot, the entire AI research. And that's what happened in 80s. a reboot happened, which said that forget all these grand challenges. Let's use the computing power. Remember, the computing power kept on evolving or increasing quite rapidly, and also the storage power capacity kept on increasing quite rapidly. So let's use this additional storage space and computing power to do some intelligent tasks well. For example, what were called the expert systems, they were built by using human knowledge repository, let's say for diagnosing a specific illness. So there is an entire human repository of knowledge there, which is taught in the MBBS and other domains, that look at the symptoms. If these are the set of symptoms, then it's likely to be this illness. And so there is a very stepwise process which is described, and that was very amenable to being done on a machine, except that it required a large amount of repository, which was now feasible. Along the similar lines came quite a significant success, which was Deep Thought, which was an IBM computer designed to play chess. Chess was an activity which was thought to be very amenable to computing solutions. It was not complex, it was fairly complex, but still very precisely defined. And the hope was that we can have chess game or chess playing programs which can beat humans. It didn't happen here fully, but the Deep Thought as a chess player became the first computer grandmaster of chess, which is quite a significant achievement. It means that it can actually play the chess very well. It can beat essentially all of us sitting here. I don't think we have a chess grandmaster sitting. Am I wrong? Probably not. Okay. Okay. Another very interesting development which took place in 80s was this discovery of backpropagation algorithm. Its impact has been felt only recently, but this discovery was very significant. This essentially is an efficient algorithm to train neural network. Remember, I talked about when there are a large number of neural networks, how do you get those weights? This algorithm showed how to get those weights in a fairly efficient way. Still, that was not efficient enough to scale up to very large number of gates, but a few hundred gates could be trained using this. So, some more tasks could be done now using neural networks. But this decade ended essentially in more disappointments, based on the hope that increased computational power is going to now take us to solving some grand problems. And this was primarily funded by the Japanese government. They came up with this 5th generation computers idea, which can do again the same earlier thought that they talk like humans, they can reason like humans. So, but that just failed to take off despite quite significant funding. That was also the beginning of the personal computers era. And in that, somewhere in that transition period, the focus shifted from building special purpose large computers to general purpose small computers. So there was this entire shift in focus also took place. So that kind of got lower and lower priority. Anyway, not much was happening there. Then we come to next 2 decades. These were decades of steady progress. Nothing spectacular, but good progress. For example, the successor of Deep Thought, called Deep Blue, bet the world chess champion, Garry Kasparov, in 1997. And that was achieved simply by throwing more computational power and more memory at more or less the same thing. And that, like I said, the computing power has been following what we call the Moore's law, which says that the computing power doubles every 1.5 years roughly. So just from 60s to 90s already, in that 30 years, one had, according to Moore's law, a million factor improvement in processing speed. And just that additional power allowed this Deep Blue to analyze much larger number of moves before it makes that. And with that, with of course certain algorithmic techniques also, it could beat Kasparov. 2007, another milestone was achieved when a CMU designed autonomous vehicle, which is not has any human guidance, drove for 90 kilometers in traffic without colliding. So that's also a very complex task, because it has to do a real-time analysis of the video, the audio that is coming in, and based on that make certain mechanical decisions. In parallel, while the computing power grew up, also what improved is algorithmic prowess. More and more algorithms were discovered which were very clever and exploited the structure which lied in the problem in an efficient way. So while the computing power increased, also the ability for algorithms to do more or more efficiently the same thing also increased. So just these two multiplied together to really give a much more compute power or computational ability at our hand. One very significant development that took place was algorithms to solve even NP-hard problems. I mentioned that NP-hard problems are the ones that you cannot hope to solve efficiently, which still holds the case. But what these algorithms did was to solve special cases of the NP-hard problems, and these special cases were general enough to encompass a large number of real-life problems that we want to solve. The biggest type of these algorithms are what is called SAT solvers. Now, SAT or satisfiability is perhaps the most fundamental NP-hard problem. It is the canonical NP-complete problem. It is simply a coding of finding a solution under certain simple constraints that are specified. Let me just give an example. Suppose you want to find a complete pairing of n boys and n girls, one boy with one girl. Given the constraints that some pairs are compatible with each other and some pairs are not compatible with each other. So you want to find a compatible pairing. This problem we can code as a satisfiability instance in the following way. Let xij denote a Boolean variable indicating whether boy is paired with girl j. Boy I is paired with girl j. So xij takes a value 1 if boy I is paired with girl j, otherwise it takes a value 0. The constraint that we impose on this is that if you look at all compatible pairs ij and look at the OR of the variables xij, it must be true. And look at all compatible pairs ij and run over all i's and take the OR of xij, it must be true. This is coding the fact that that boy number I must be paired with at least one girl. Similarly, the OR over j of the same set, this is coding the fact that every girl must be paired with at least one boy. Next come the constraints which say that xi1j and not of xi2j is true, or not of xi1j and xi2j is true. when I1 is not equal to I2. This is quoting the fact that no boy is paired to more than one girl. Similarly, no girl is paired to more than one boy. You patch together these three classes of constraint, a solution to this gives you this pairing solutions. So we have transformed the problem into a what we call a SAT instance, where there are given Boolean variables and there are conditions coded by ands and ots and nots, and you want to find a solution to all these conditions. This is an NP-hard problem, as I said, but these SAT solvers find very efficiently solutions to these instances when the instances come from a certain class of instances, not all possible instances. So the SAT solvers started being very useful in the intelligent tasks. Remember, I said that number of intelligent tasks are NP-hard problems. So we want to transform those tasks into a satisfiability instance, apply SAT solver. If you happen to fall in that domain, then you get the solution fairly quickly. So this started getting developed from 90s onwards. SAT solver, they started getting better and better over time, and they could handle a large number of problems, provided you do this transformation of that problem into a satisfiability instance somewhat cleverly. Okay, so with this all in place, this steady development up to the beginning of this decade came the Big Bang. In last 10 years, there has been phenomenal progress in solving intelligent problems, the problems of human intelligence. The central reason for this is coming together of two very different streams, which are kind of started for different reasons in computing, but they got together. One was increase in computational power, more specifically computational power of certain kind, which is of doing matrix operations. Now, I'm sure everybody here has learned about this fabulous computer games that exist today. It has such a tremendous market since last 20-30 years that enormous resources have been spent in developing better and better gameplay. And this at some point in time led to the invention of GPUs, which are short for graphical processing units. These were specifically designed to do matrix operations very fast, because the entire gameplay, which is a lot of visuals which you want to change over time very rapidly, and this change is essentially captured by a matrix transformation. So you can do that change of visual, that entire visual display very quickly if you can compute matrix operations quickly, and that is what led to the GPUs. The second one was the invention of internet. Again, it happened in 90s, and with the internet came data, tremendous amount of data. Not only random data, but also, of course, random data was also there, but also was data which was annotated. Take, for example, Wikipedia. There's a huge collection of data annotated by a very large number of people, but it collectively makes a huge repository of useful information. So, these two things together, that is availability of large amount of annotated data, along with this GPUs which did matrix operations very efficiently or very quickly. If you go back to that machine learning or this neural network training part, it requires this input-output behavior, which is nothing but annotated data. Also, it required the learning of weights, which is, as I said, was really a matrix operations. So with these two together, one could actually do learning on a large input-output set very efficiently. So suddenly the number of gates that you could handle and number of levels you could handle blew up by a very significant margin, by 2 orders of magnitude actually. This large networks, neural networks, and training them is what is today called deep learning. Deep stands for large number of layers that are possible today. And this led to a quantum jump in the kind of, or the quality of solutions that we get. Literally, deep learning has been outperforming just about any other AI technique in many domains, like hidden Markov model, support vector machine. These have been developed over a period of time, but this deep learning has been kind of replacing them at many of these places. It's now become almost pervasive. Some examples of success of deep learning. In 2011, in a visual pattern recognition contest, first time the deep learning based algorithm bet humans. 2012, this ImageNet is a massive repository of images, and they run this regular competition of classifying those images. And a deep learning based algorithm bet all other algorithms by a very significant margin. 2015, development was led by Google, who have been working on speech recognition for quite some time. And a deep learning based algorithm of theirs gave 49% improvement in the quality of speech recognition. And in fact, this is what made possible today when all your smartphones and so many other devices can carry out very efficient speech recognition, very high quality speech recognition, is because you have a deep neural net sitting somewhere in the phone. Well, this is a development which I'm sure all of us are aware of. These autonomous cars developed by Googles and others today are extremely competent machines. They can literally do as well as humans can. In biology, again, very significant achievements. There was a molecular activity challenge to predict a biomolecular target of a drug. Again, this challenge was won comprehensively in 2012 by a deep learning based algorithm. Similarly, MICCAI challenge on analysis of large medical images for cancer detection, won by this. Deep Patient in 2015 was designed which could predict, again by analyzing the patient data, the onset of liver cancer, schizophrenia and such diseases. It achieved tremendous success. In fact, today these algorithms routinely outperform human doctors in such analytics. Deep learning in games. Chess was already done and dusted, so the attention moved on to more complex games. One of them was Jeopardy. IBM designed computer Watson bet 2 best humans players in the Jeopardy. This program used essentially Wikipedia as its primary source of information. Go is a much more complex version of the chess, and it was believed that while chess was conquered in 90s, it would take many decades before computers can beat a human or a good human player in a game like Go, because it required formulation of strategies, for very complex strategies, and carrying it out over a long number of moves. And that's what specialized the winners. That expectation was obliterated already in 2016 when Google's AlphaGo algorithm bet the reigning world champion in Go. And this current reigning world champion is considered one of the greatest players in the history of Go playing. I'm almost done. Then within a year, Google came up with a new version of AlphaGo, which did not start with any initial data. So the first one was trained by a lot of Go games which were annotated properly. The second version did not start with any annotated data. It started completely blank and started playing games and kept on learning by playing games. And after a few million games it played, it became so good that it bred the previous version of AlphaGo, the last year's version, 100 nil. This was based on what we call now the reinforced learning, that you learn, but you start with a blank state, you start doing the activity, and that feedback gives you ability to fix those weights, and then you keep improving yourself. I have just touched upon the deep learning because that's been the most important influencer in this in last decade. But this is not the only technique that exists today. There are Bayesian learnings which uses a lot of statistics to predict the value of influencing variables based on the outcomes. Clustering, which detects patterns in large amount of data. These techniques have been used in a very interesting way in social networks, where the society is modeled as a large network of connections, and then you discover clusters and other structures in it, which today is leading to understanding of behavior of society as general. So the domain that is getting impacted by the modern AI techniques have been now not only science, but humanities, economics, and so many others. So this is where we are today. What does the future hold for us? Well, the computation speed is continuing to follow the Moore's law, despite some predictions that it will stop at some point. It will stop at some point. It can't go on doubling forever, but that point is still in the future. Today is still doubling the speed with roughly the same speed in the same time. Now, methods based on this deep learning are continuing, as I said, to expand into newer domains with becoming more powerful. The reinforced learning based methods are also now coming up, which is also a very remarkable thing, that you don't have to train, you let it train itself. SAT solvers are continuing to improve. They're getting better and better, solving larger and larger class of SAT instances. These newer methods like Bayesian learning, clustering are also making great advances. And these are all converging. So they are being applied independently, but are getting applied together. And it's clear that computers will outperform humans in more and more tasks. They can, get better and better in doing certain specific things, and leave us far behind, really. Also, this large amount of data that we are collecting in just about every domain is going to lead to better knowledge about the structures through these learning methods, and lead us to newer insights, which normally we won't be able to get. So that's where we are certainly going. But one has to be mindful of the hype, and again the new hype, which is same as the old hype, which is doing rounds, is that there are again years, or a prediction is being put, like by 2050 computers will become more intelligent than humans. So this new species of super intelligent beings will take over. But there is something fundamental missing even today in the computer-based intelligence. We have phenomenally good algorithms for solving specific tasks, and they are getting better and better. However, a human brain is one single algorithm, a large algorithm, if you will, which can solve a very large number of tasks in a large variety of domains very well. Today, there does not exist a single computer algorithm which can do this. That is, multiple tasks in multiple domains, all handled by the same algorithm. And it is not even clear how to do that, because this training model, you train the network, then you kind of fixing the weights in a way to solve something specific. It is not clear how to generalize this to solve very different things together. And that's where the next challenge of research lies, that how do you make that happen? It's not even clear whether the current direction in which we are progressing will lead us there. It may happen, but it may not happen. And most certainly this current hype that we are 2040, 2050, this is going to happen is not going to happen, at least in my view. But we are at the same time at a very exciting stage in this development of artificial intelligence. We are seeing today literally the fruits of the progress of last 60 years, because most of the things that are giving us results today, the foundation was laid in 60s and 70s. It has gone through a lot of ups and downs. We are really on the up today, and hopefully it will lead us to some very significant development in the future. Thank you.